So, in case no one has heard the news that we were talking about, we are having water rationing here in Lincoln. The reason is not because our water is tainted. You don't have to worry about the safety of drinking water yet. But Lincoln's wells for the municipal water are out near Ashland, and their wells are now underwater, and they've had some disruption in the pumping and having a hard time getting as much water as Lincoln uses. So that's why we have water rationing. DJ.
What does all the flooding also mean for the cleanliness of our water?
That was what I said. It's not effective. The water cleaning process is not in the regions that are flooded.
Okay.
And so those plants, once the water gets there, there's no problem. It's just that the pumps themselves are underwater. Which, it's one of the funny things about a flood. You've got water everywhere and none to drink. I don't know if you guys have seen how bad it is, but it's pretty brutal out there. On Saturday, we went out to see the Platte River, and I've never seen the airplane flying over water out there. I've never seen water in the second part, apparently, of that bridge. I've only seen the first part where you normally see water going. It's really flowing. Michael, do you have some?
Oh, no.
Yeah. What's causing the flooding?
Melting snow.
Largely melting snow, right? It's not been raining, but we had a lot of snow this winter, and all of a sudden it turned warm. Yay. Spring starts in, was it 2 days? So I propose that we have spring break. What do you say?
Spring already started.
DJ, who wants to can't stop.
Okay, so let's get started. We talked about microscopes last class period. What's the purpose of a microscope?
To magnify objects into images that we can see.
What kind of objects? Small objects. Where are the objects located?
Well, they're on this side, so.
On this side. The answer I'm looking for is probably not very clearly defined. Wherever we want them to be. They're small things that we can manipulate their position. Now, a telescope, what's the purpose of a telescope? What does tele mean?
I think a TV.
Okay, we can use it. It's the same word with the same meaning. Television. Vision is pretty clear. Tele. You're looking at something that's far away. So television is looking at something far away. Telephone is talking to somebody far away. In theory, I know I could call you here. A telescope is looking at something far away. So what is the purpose then of a telescope?
To scope out something that's far away.
To scope out something that's very good use of words. We're going to scope it out. We're going to look at it. Are we looking at big things or small things with a telescope?
Big things.
Big things. So telescopes, you're looking at big things. So why do you need to magnify a big thing? Because they do magnify.
So you can see the detail.
Okay, why would you not be able to see detail if it's really big? Because they're far away. They're far away, so they make a small angle. And so that small angle, we have a hard time resolving what's going on there. See how it is. Leaves class to go to the vending machine, but at least he's helping out his classmates. There's a certain goodness in that. He's just happy I see the goodness. So we're going to talk about those as well today. So a reminder on the compound microscope. The compound microscope is compound because it's got two lenses. Got two lenses, the eyepiece and the objective. Easy to know which one's which. The eyepiece is the one closest to the eyeball. The objective is the one closest to the object. Now in this picture, which one has the shorter focal length, the eyepiece or the objective?
The objective.
The objective. Those little dots are closer to the objective lens than the F's and E's are to the eyepiece. That's how you make a microscope. You have your short focal length lens, shorter focal length lens, is the objective. The longer focal length lens is going to be the eyepiece. Now, if you look at our equation here, the magnification is your near point times the total length of the microscope minus the focal length of the eyepiece minus the focal length of the objective. Now, what's the focal length? Length minus focal length of the eyepiece minus focal length of the objective. It's this distance right here. That sometimes is called an extra focal distance. That is the parameter that is in parentheses. So if you just look at this equation, what things might you consider to increase the magnification of a microscope? Want to see more detail?
Yeah.
Okay, you said.
Or no, but maybe the focusing power. Like if you curve the lenses more.
Okay, if you change the focal length, if you make them curve more, which is going to maybe have a shorter focal length, then you're going to have a bigger magnification. Now, with this equation, you might also say, well, I could change the length, right? If I make it so it's a longer microscope, I will also have a bigger magnification. Problem is, the length is also important for another thing. We like to focus our microscopes. And how do you focus a microscope in practice? Usually you're changing the length. You're adjusting the distance between the eyepiece and the objective. So you're changing that length. That's usually what our focus is. Now, just a couple more things on how the microscope works. You want the object to be close to the objective. The closer it is to the objective, the bigger the intermediate image is going to be, and thus the bigger overall magnification. And so you have a very short focal length objective lens, so you can put the object just a little bit farther than the focal length of the objective and make an image at some reasonable distance here. And then you have the eyepiece. This here is actually showing what kind of viewing is this here, where it's a real image at a finite distance away, or excuse me, a virtual image at a finite distance away. Is that accommodated or unaccommodated viewing? It's accommodated. Unaccommodated would be infinitely far away. And to do that, you would have this intermediate image right at the focal length of the eyepiece. So just some basic things. One last thing. You probably have used a microscope that has like 3 lenses that you can rotate through. What's the point of those 3 lenses?
Each one of them has a different focal.
Each one has a different focal length, which means that you're changing this number and this number as well. And so you're changing the overall magnification. And so if you have a lens with a shorter focal length for the eyepiece, you're going to have a bigger magnification. You will also have to adjust the length of your microscope to be in focus. It's not going to be the same length for each one unless they're actually placed with the lenses in different positions to counteract that. And we see the same exact thing in telescope. Here's something that you might not have thought about. The numerical aperture of a microscope. The numerical aperture is telling you about how much light you're collecting or how much you're getting from your sample. The more light you're collecting, the more you're going to be able to see. Also, you're going to be able to get better resolution. And so it's measured as the half angle. Half angle means you take what's shown there as theta and you divide it by 2. And so in the picture on the right, you see it has alpha shown. That's the half angle. That's what we measure for the aperture. And so the numerical aperture just refers to that acceptance angle, this here. Now, if we use trigonometry, this distance here and this distance here can be combined to give us tangent of alpha is this distance over this distance. So it's not a big calculation. I'm not going to test you on this. But I want you to know what it is, so if you're using a microscope and you see what the numerical aperture is, you have an idea. Ah, yes, this one has a bigger numerical aperture, which means it's going to be able to collect more light and probably have a better resolution. Now, we'll learn about the resolution in the wave optics section, which we'll talk about in lab tomorrow. Oh, wrong way. Things you can do to make life better. Has anyone ever used an oil microscope? A microscope that you put oil on your slide? Okay, we have some that say yes. That oil is for a real important purpose. It allows you to increase your numerical aperture. Because if you look at this picture, you typically have a cover glass covering your sample, I suppose in biology or something. I'm a physicist that don't have a lot of experience with this. And then the light is going to refract out of that glass. And so the actual angle coming from your sample that you're accepting is going to be the angle right here. Right? Yeah, this is spreading out nicely. But what you're accepting is just this. Any light that came out like this, it's gone. But if you put something like, let's say, water, you had a water immersion microscope, then with the water, it would refract something like this, and so you would have a bigger angle that you're able to see. And if you put oil immersion, something that has an even bigger index refraction, you might have it go like this, which means that you could have light coming like this and still make it into your lens. And so what you're getting with that oil immersion microscope is you're able to increase the numerical aperture. You're able to increase the light coming from the sample that you can see. And at the same time, you're increasing the possible resolution you can get. And I know we haven't talked about this, but one more thing that has to do with resolution. Has anybody used a blue microscope? Nope. Another thing that limits the detail you can see is the wavelength of the light. Longer wavelengths, you can't see as much detail. And we'll get into this in this week. Shorter wavelengths, you can see more detail. And so some microscopes are made so they use blue light because that's the shortest visible wavelengths. And thus, you actually can just about double the resolution going to blue light compared to red light. So you'll have some microscopes that use blue light to give you better resolution. And then later on, we'll learn about electron microscopes that allow you to have even better resolution because you have an even shorter wavelength. And right now, you should be saying, but electrons, they're not light. They don't have wavelengths. Louis de Broglie, let's pronounce his name right for Christ's, for criminy's sake. Excuse me. I don't even say that ever. I don't know why. He said, why shouldn't an electron have a wavelength just like light? Okay, telescopes. Here's two different types of telescopes. This one down here is your standard Newtonian telescope. Lenses. What types of lenses do I have in this lower telescope? I have two converging lenses. The first lens is closest to the object. What should we call the lens closest to the object?
The objective.
The objective. The second one's closest to the eye, so we call it the eyepiece. Now, in this picture, your actual object is way out here, right? It looks just the same. And the objective lens is making a real or virtual image? It's making a real image. It's real because the rays really came together there. If we go back to the picture of the microscope, was the microscope making a real or virtual image here? No, it was real because the rays really came together there. The intermediate image was real in both cases. Now, the final image here was virtual because these dashed rays, those were not the actual rays. If we look at the telescope, the final image is once again a virtual image. It's not the actual rays meeting. So the telescope, just like the microscope, is taking an object, making a real image, and then from that real image, you make a virtual image. It sounds like the same thing, right? Fundamentally, it is. The difference in the microscope and the telescope is, for the microscope, you have the object really close to the objective. For the telescope, it's really far away. Now, if the object is really close to the objective, where's the image going to be formed? 1 over f equals 1 over distance object plus 1 over distance image. As distance object approaches focal length, what's happening to distance image? I'm going to write these equations down. So as distance object approaches the focal length, what is 1 over distance image approaching? Yeah. 1 over distance image is approaching 0, so distance image is approaching infinity. So in the case of the microscope, as you bring the object closer, the image position is moving farther and farther away. But in the telescope, you push the object very far away. So if, for the telescope, you have, so change colors here. What is 1 over distance image approach? Okay.
Oh, we're saying that distance object is equal to 3. What is distance image equal?
Yeah.
Whatever the focal length is.
So for the telescope, the image is going to be formed essentially at the focal length of the objective lens. This actually makes our calculations much simpler. We have, notice the magnification of the objective lens. It's just 1. Well, it's just 1 as we look at it here. It's not 1 in the end, but it's just 1. And then we're going to have the this intermediate image is at the focal point of the objective for unaccommodated viewing, for relaxed viewing. Makes the image infinitely far away. And we want to calculate the magnification again. Now the magnification, just like before, we're going to calculate the transverse magnification. I'm going to move up here. Magnification transverse from the first lens. That magnification is height of the image over height of the object, right? Well, this becomes a little problematic. Distance objects is approaching infinity, isn't it? So that's kind of going to be rough for us because we're going to say, well, that's approaching 0 magnification. That doesn't work out, right? So what we're going to do is we are going to say, well, what's the angle that this would have made with the eyeball if I didn't have the telescope? If I didn't have the telescope, zoom in, this angle right here is the angle it would have made with the eyeball. And looking at my picture, since this image is formed at the focal length of the objective, then I'm going to have tangent theta unaided, you can tell I'm really zoomed in, is equal to the height of that image over the focal length of the objective. So that's my unaided angle. Now, if I look for my aided angle, and this picture is not showing for unaccommodated, but I'm going to do it for unaccommodated. If it's unaccommodated, I would have had this distance here would be focal length of the eyepiece as well. it'd be the height of the image over focal length of the eyepiece. So what's my magnification? Theta aided over theta unaided. Small angle approximation, how do I go from tangent to the angle? Okay, inverse tangent is always correct. But small angle approximation says that the angle is approximately equal to tangent of the angle. That's only in the case of a small angle. But our telescope is clearly working with small angles. Otherwise, we wouldn't need it. And so for small angles, that's just going to be theta aided was height of the image over focal length of the eyepiece. Theta unaided was height of the image over focal length of the objective. There is one more thing that I did not play careful with. This is an inverted image, right? And so I have to throw a minus sign in because of that inversion. There's the equation for magnification of a telescope. That's a lot easier equation, isn't it? Now that's the magnification for unaccommodated viewing. And you know what we're going to do in life? We're going to stick with unaccommodated viewing for the telescope. We're not going to worry about what accommodated viewing would be. So it's easy calculation. Feeling good about that? The next one is just as easy. The length. I didn't even go through the calculation for the length of the microscope, but for the telescope, it's real easy. For the telescope, remember, we're going to put these two things on top of each other. That is, the image is going to be at the focal length of the eyepiece. So focal length of the objective is at focal length of the eyepiece. And so the length is focal length of the objective plus focal length of the eyepiece. So there are the two equations for a telescope. The length equation is the sum of the focal lengths. The magnification is the ratio of focal lengths. What does the minus sign indicate? Inverted. Now, if an astronomer is looking at a telescope, the astronomer does not care. She can look at that and she just says, I need to slew the telescope this way, and does it. If you were using this to watch like runners in a race, you're looking at the runners going that way, what direction would you naturally want to move the telescope? That way.
Sorry, I can't search the web on Apple Watch.
Good. Since it's muted and all, but the fact is, if you're using a telescope and it's inverted, if you see them going that way, you need to go this way to follow it. And that would be a little confusing, wouldn't it? So this kind of telescope is great for astronomy, not so good for terrestrial viewing. If you are trying to study the condors in a nest over there, you don't want to invert it. So that's where we get this upper one, which is a Galilean telescope. What's different about the Galilean telescope? It has a diverging eyepiece. And that diverging eyepiece is going to make it so you have an upright virtual image instead of an inverted virtual image. The intermediate image is actually going to be formed back here. So the intermediate image is at a negative object distance with the Galilean telescope. What's really happening, you don't actually form that intermediate image, right? Because the light gets bent, but it gets bent as if you had your object at that location. So that's the difference. Now, who invented the telescope? It's a trick question that I expect Leslie to answer. Okay, anyone besides Leslie? Galileo's grandchild. That was a really good guess. a lot of people think, oh, Galileo invented it. And that's not true. Galileo heard about this new invention. It was a party game. Somebody said, "Woo, look at cool things with this." And Galileo went rushing off to try to buy one, but the traders from the Netherlands, or whatever, I don't remember what the name of the region was called back then, like the Flanders or something like that. The Flemish dudes were gone. But he got descriptions, and then he made his own, and he improved it. So Galileo didn't invent the telescope. He improved it, and he was the first person to use them to make systematic observations of the stars with them. Right? The inventors, these were a cool party thing, like a kaleidoscope type thing. Something fun to play with. And something that's really interesting I've got to throw in there. When Galileo was using his telescope to observe the heavenly bodies, like, Saturn, seeing the phases of Saturn, seeing the rings around Saturn, Jupiter and discovering the Galilean moons around Jupiter, the sun and discovering the sunspots, and going blind. He invited other people to look through his telescope. And some people refused. They refused because this was likely a tool of the devil that would beguile them and show them something that was false. Nathan's just agreeing. Yep, that's why I don't use a telescope either. Just an interesting little fact there. So we've got these telescopes. The purpose is to view things that are far, to magnify them to bigger angles. So let's do a problem. So once again, I'll have you guys work on this as groups. You have a telescope with an objective lens with a focal length of 1 meter. You always want the objective lens to be the long focal length for a telescope, whereas the objective is the short one for a microscope. And an eyepiece with a focal length of 5 centimeters. How long is the telescope? What's the angle of magnification? What's the easiest way you can change it to increase the magnification to 50 times, and how long would the telescope be then?
That isn't a lot of things.
It's a lot of questions, but it was, actually I won't rewrite, I'm going to copy and drag. Okay, wait. Okay, so there you have your equations.
Sorry, Dr. Webb, I didn't know how you invented it. I just knew Galileo made it better. That's all I knew.
Yeah, it's okay. It's okay.
Wait, who said it? Okay.
We don't know. We just
Yeah, there you go. Okay. Now there's a reason for that.
You have this misremembered history. And this can be true. That's what I was taught. It doesn't have to be false. It's just the Lord doesn't have whether it's true or not.
Oh, well, that lore is based on some history that somebody doesn't remember very well.
0.2. FE is still on the items. Okay, so the first one was 20 millimeters.
Did he need to put a divided by on that thing?
Oh, yeah, the divided side. I erased that one. I erased the circle and apparently caught the divisor as well. Thank you.
I saw it with the divider anyway. You're not going to hear that again?
What's the magnification?
How long is this?
No, this is magnification. 200 times. This unit works. It's 200 times. We're good. We're good. This is when you can change. Right.
Wow.
Okay, so Ryan has the first two answers. Just let me tell you what to do.
Oh, I'll type it to you.
0.05. 0.0. Yes. You didn't do that.
No, that's why I did the first one. I got that. And then you said no.
It's plus it's 20. We're good.
Okay. What kind of conversation? What kind of conversation?
Well, let's have a conversation after we answer the last question. It's 20 times. Now we're gonna get to 50 times.
What is easiest?
Well, it's asking how long something just takes our life. That's what kind of we do.
That's not gonna increase change magnification. You won't have the magnification.
So you could. You would change the eyepiece.
Is it the easiest?
You want to change the focal difference.
Yeah.
I'm not sure.
There's no easy.
That's what I mean. I quickly objected to
We can change my
closer to our group.
Or you can just switch eyepieces. That's what you do.
Oh, it's just the.
Alright.
Yeah,
So
I was
going
like,
all the
it
way
does say
up.
the
How
easiest.
far away is this? Well, if I'm changing that.
Not the
and walking
best,
back
the
in here.
easiest. Okay.
DJ.
So why would changing license be the easiest?
Yeah. So we need to change it to this indicates 1.0.
What's negative?
The length is not as good.
The negative indicates that it's in.
So do we need to
Wait,
find
Our
so-
nose, great.
So wait,
Our nose.
Okay, yes.
You're my scribe.
When I said 50 times, I meant the absolute value is 50 times.
Absolutely not.
Sorry about that.
So why are we changing the eyepiece?
Easiest?
Because you just swap that it or?
telescope five?
Well, because if you change the length, it
No,
doesn't
not five.
do anything. You can't see it all.
Yeah.
So you have to change. Use the glasses. So
The length of the telescope.
you have to change the movie. Those are the only things in the equation anyway.
Yeah.
So the eyepiece is
I
right
just thought it
behind
was
it. You know, you can touch it. The objective is like all the way over there.
Yeah.
So it's easier to change the eyepiece than you change your objective. You go over there.
That makes sense. At first I didn't really correctly. I thought easiest is the best. What would be the best? But no, the easiest is like
I
eyepiece.
wish the easiest was always the best.
You got it.
So
Okay, I think we've all got the concept, if not the answers. So let's go through the work here. Magnification. First, let's make sure we identify our values. What is f sub o? Which has a length of? And what is f sub e? Okay, so I'm going to go ahead and put them both in meters, following trace. Now we just put our numbers in. Magnification equals minus focal length of the objective, 1.00 meters, over focal length of the eyepiece, 0.0500 meters, which is minus 20 times. Now the minus means it's inverted. We usually just say 20 times and don't worry about the minus sign, which is why I forgot when I said what would it have to be 50 times. But technically minus is the correct value here. It's minus because it's inverted. And then the length, how many sig figs do I have in my answer?
3.
Yes. Because you take the greatest of the least significant digits, And the least significant digits were this one and this one. This here being in the 1/100ths is a bigger place, and so my answer was good to that place. Okay, so there were my original answers. And then we had the part that required you to do analytical thinking. What's the easiest way? There's more than one way to do this. The easiest way, you have magnification is just the ratio of the focal lengths. So what's the hardest way? The hardest way is, let's get a new objective and a new eyepiece. Right, that would be the hardest. The easiest is to change the eyepiece because it's the small lens. Bigger lenses are harder to change than small lenses. So the easiest way is to change the eyepiece. And so if we keep the same focal length for the objective, and we have magnification, I'm going to put a prime for the new one, is equal to, I'll put the minus 50 here just so I've taken into account that I'd use absolute value, equals minus the focal length of the objective over focal length of the eyepiece prime. And I saw that for focal length of the eyepiece prime. .00 centimeters. But if I put this 2.00 centimeter lens in, I'm going to have to change the length. So it'd be 1.02 centimeters long. Now, does anyone here actually have a telescope that they use?
I do, but it's at home and I don't know much about it.
Okay. Well, have you ever changed the eyepiece? No. I'm not going to bring it out just because I don't have it out here right now. But when you change the eyepieces come from being little guys like this, that are about this big around, to being things that are like this long and this big around. Why are they different lengths? Because you're going to have a different length for the telescope, and so they mount the telescope on a piece of tube to extend it out how far that one's going to have to be compared to the others. So you have a different length of the telescope for the different eyepieces, and they make the eyepieces have different lengths of the tubes, so the telescope itself can stay as it is. You just put in a different eyepiece, and it's close to the focal point. And then you focus it by moving that eyepiece in and out a little. So the length is an important factor, and I want you to understand why the eyepieces don't look the same, why they don't all have this height, because they need different distances to make the total length match up. And the lower magnifications are going to have longer focal lengths, and thus it's going to have to be a longer telescope. So Galileo had a solution to give you an upright image. But it's not the only solution. So here's another one. Now, I don't hunt, but if I did, I would certainly have a scope on my rifle. And that scope is going to have a little graticule in there. That is a little thing that has horizontal and vertical lines and maybe a circle and a dot. And I say, ooh, if the bullseye, because I would never be hunting animals. If I was using this thing, I would be hunting targets, non-living targets. Now, I want the bullseye to be there in that circle. Well, how do they make that happen? You ever think about that? How do they make it so you have that little graticule thing that's in focus as well as your target being in focus? They're clearly not the same place, are they? Well, what they do is what's shown here. You don't have to have a field lens to do it. But what you have is, even with the other design, you can do it, but it'd be inverted. Nobody would want it, right? If you have this design here, you can have the graticule here, and you'd see the upside down picture of the deer from the target, and it would just feel wrong, especially because when something's farther away, you're going to have to shoot higher because gravity's going to make it drop. And that would seem really weird. I have to shoot closer to the hooves to get toward the center body mass. You expect to be shooting above it, not below it. So what we want is that thing to be reinverted, and we do that by the use of a field lens. Here it's called an erecting lens, erecting to make it upright again. So an alternative name for this is the field lens. And so in this case, you have an intermediate image at the focal length of the objective, just like normal. And then you have a second intermediate image for unaccommodated viewing at the focal point of the eyepiece. And so that field lens is inverting it. It's adding to the length, clearly, of your telescope. So putting in that field lens is going to have to make the telescope longer. In this case, you can see that the distance here is shorter than the distance here. And thinking back, magnification if the distance image is longer than the distance object, it's magnifying. So in this configuration as shown, you're getting some magnification from that field lens. You're making it a little bit longer to get magnification compared to what it would be if it wasn't magnifying, but you can do that. So where do you put the graticule? You put that graticule either here or here. You put it in one of those image planes. The image plane is where everything comes into focus. If you put a piece of glass there that has your pattern marked out on it, since you're focusing on the image that's in focus there, you're going to see both of them overlaid. And so that's how you can have them overlaid. Now, I talked about aiming. This is going back to first semester. What does a real person do with their sights if they're going to, I'm aiming at something that's 200 meters away? What do you do with your sights?
Just for other factors like wind and stuff.
Okay, aim high is what you do if you had a fixed sight. But what they do is they adjust the sight, so instead of being parallel with the barrel, it's going like this. So you're sighting like this, and it's launching the bullet, so it's going to go up and drop back down. And given how fast the bullet's coming out, the acceleration of gravity, and the distance, you can calculate how long it's going to be in the air, thus how much it's going to drop from the straight line, and how much you need to adjust. And so with those, they are going to have it adjusted so you are aiming at what looks like center mass to hit center mass. The bullet's coming out above, comes back down. Now what about, we watch TV and they've got the laser sights. What about that? If you're hunting at a distance, you have to adjust the laser sight in the same way, right? But on SWAT, they never do that. Why not? Okay, it's a TV show, that's one thing. By the way, you guys seen the TV show, The Rookie?
I saw the trailer. It's like Castle.
You all have to watch it because one of my classmates and friends from college is the producer, Helen Pine. She was also a co-producer of Gilmore Girls. She did Grimm or whatever, something really crazy. Anyway, totally off topic. But in something like SWAT, they don't worry about it because you know what they're shooting? They're shooting people who are like 10 or 15 feet away. How much is the bullet going to drop in 15 feet?
Not very much.
Yeah, not very much. So they don't have to worry about adjusting their. They just keep it parallel to the barrel, and they're pretty much going to hit whatever the laser's on. Because light travels as a, this is going back to the beginning of this section, as a ray, a straight line. Wow, time flies. There are other telescopes. This here is not correctly attached because I believe his name is Mark Cassini. He and his group, for their group project, decided to make a telescope, and they use this as the objective because it's a big mirror. not a very well ground mirror, turns out, not ground at all. They use this. Well, to make a telescope with a mirror, you're going to have to change your optics a bit. Because instead of having an objective lens, you have an objective mirror. The light reflects back. And so one design is to put a mirror in the center here and reflect it off to the side. That is, actually I call this a Newtonian telescope. Actually, I think Newtonian might be a reflector. I might have been wrong. God forbid. But this telescope here, notice the eyepiece is still a lens, but you have an objective mirror. There's some real benefits to having a mirror rather than a lens. For starters, when you make a big lens, that lens is going to be heavy. And if you just support it around the outside, it's going to sag over time under its own weight. You have to grind two surfaces on the mirror. The mirror is made of a glass that's going to absorb some light, and also you have the dispersion relation, different focal length for different colors, which means that your telescope that uses a lens for the objective is going to focus different colors at different locations. We call that chromatic aberration. Aberrations are errors in the image. If you use a mirror, the mirror can be made on a thin surface. You only have one surface to worry about. You coat it with something like aluminum or silver that's very highly reflective, has exactly the same focal length for all colors. The focal length, by the way, for a mirror, I don't think I ever said this. For a mirror, the focal length is 1/2 the radius of curvature. So it's pretty simple. So it's easy to support, easy to create, good reflectivity, no difference in colors. It's a better design. But of course, you have a problem. The obvious problem is light from my object that comes in here gets dropped. We don't have that. It's not as big of a problem as you might think. We talk about the light gathering power. How faint the objects are they can see. It's proportional to light gathering power. And that's just the area of the objective. We have a special term for the area of the objective. So that's going to be pi times the radius squared, right? Area of a circle. Well, if you have this blocked, radius blocked, and radius of the objective, you would then have the light gathering power for mirror LGP is equal to pi radius of the objective squared minus pi radius block squared. Since it's squared, if you make it kind of a small radius, it's going to be a small percentage of your total light. So it's not as big of a problem as it seems. Now this here is not the standard telescope. We have two telescopes back there, and they're both what we call a Schmidt-Cassegrain design. So here's the Schmidt-Cassegrain design. You start with your telescope. And back here you have your objective. At this point, it seems wrong because your object is out here. And your objective is as far away as you can get from it. But the objective is the first thing the light hits. And so what's going to happen to light when it comes in? It's going to reflect back like this. Well, inside of this, there is a second piece. There is a glass cover here that has a mirror in the center. And so the light comes and goes like this. And now you're like, okay, you've blocked some light there in the center. It's coming back and it's hitting the center of this mirror. Perfect. That's exactly what I just had. The mirror has a hole in it. And then on the other side, so the light comes through here, And on the other side, you have either an eyepiece or a final mirror here. Usually you put a mirror like this and you put your eyepiece like that. Now this has another really big advantage. The light path is folded on itself. The distance the light has to travel from the objective to the eyepiece is that, and then plus this small distance here. Effectively, the length of the telescope is equal to 1/2 the length of the focal length of the objective. So you're able to make your telescope shorter, and you have that nice big collecting mirror. This is the design that is used in most telescopes today. So if you look at the Hubble Space Telescope, it's this design. If you look at the Webb Space Telescope, it will be this design should it ever be launched. It's supposed to be in the sky right now, but it's been delayed for another couple years. They use this. There's some other positives, but I'm out of time, so I will stop there.